when chemical reactions take place in front of you, something's happening. Now, you don't always see that something happening, but if you have paper burning, for instance, you have heat and light given off, and it's fairly obvious. And we looked at the common indications of chemical reactions. And so, like, that happens in front of you. At some point in time, you're going to have to convey that information to someone else. Like, how can you describe how a chemical reaction is taking place in writing? And I think the most intuitive way for us is to kind of brute force a translation using words, all right? So we have literally what is called a word equation. And I'll abbreviate equation from here out just like everything else. And in the word equation, you're writing out the chemical reaction, or you're describing the chemical reaction as a sentence, right? So the reaction is described as a sentence. So an example of that would be a very common reaction in chemistry classrooms, which is hydrogen gas and oxygen gas reacting. And it's really cumbersome to write out a word equation because you're writing out a sentence with a bunch of words. And that's why we kind of see long-term the need to translate it into a different language of symbols and everything else. So a sentence of that would be like hydrogen gas and oxygen gas react to yield water vapor. All right. Now, one of the things that we know from the English language is that you can change order up. So you might see something like water vapor is formed from the reaction of hydrogen gas and oxygen gas. And then there's additional things that you could put in there in terms of balancing, which is going to be a very important topic. And then you can change different words here, like react to yield. You might just say yield, right? Or you could say produce, or variations of that. So our word equation, literally a sentence. There's all kinds of different ways that you can write that. And something of note is it may be qualitative or quantitative. All right. This one, as written, happens to be qualitative. That's a good description, but it's not necessarily going to help us when we're coming up with some stoichiometric ratio, right? An actual recipe for the reaction. So it may be qualitative or it may be quantitative. All right. Now, the second equation has to somehow speed things up. And one of the things we've studied is chemical formulas and chemical symbols or atomic symbols. And so we can speed this up tremendously by using a shorthand notation like that and writing a formula equation. All right. And in a formula equation, you're using symbols and formulas for compounds. So we're using symbols and chemical formulas. All right, so that time spent with nomenclature, turning names into formulas and formulas into names, and describing compounds with empirical formulas and molecular formulas and everything like that, pays off as we use some shorthand notation here to describe the chemical reactions. And so I'm going to write it out, and then we'll talk about specifically some common symbols here. But in a case like this, you have hydrogen gas, and I want to make that a little clearer, and oxygen gas. And later we'll talk about why there's a 2 there, and these react to yield water vapor. All right, and over time that water vapor will condense as liquid water, but that's not a super big issue for us. So this, again, may be qualitative, and the formula equation is generally going to be qualitative. And the problem with that is, if you look, like 2 hydrogens, 2 oxygens, 2 hydrogens, 1 oxygen, like we broke the law of conservation of matter, which isn't really acceptable. So we're going to have to deal with that. So I'll make a little note here. It's, and I'll put it in quotes, qualitative. And it's qualitative until we make it quantitative, and that requires a little extra work. So it's qualitative when it is unbalanced. Okay, and that's an important vocabulary term when we're talking about chemical reactions being balanced. So I want to look at some common symbols that you see in chemical reactions, and then I want to talk about our balanced chemical equation, and then we'll be ready to look at specific types of chemical equations. So common symbols as we look at this, you've seen some already here. Right? When you see an arrow, right, that's react to yield. Right? Or yield, or produce, or whatever, right? And you can modify that arrow a bit by adding things above it. So a common way to do that is you might put something like electricity. And that's a situation where you have electricity used in your chemical reaction. Like generally we see that with electrolysis reactions. You may see something like the arrow with a triangle above it, right? And that means that you have the reaction is heated. And so the little triangle, like historically, that's just like a caveman representation of a flame, right? And then a very, very common one that we see is when somebody puts the formula of some catalyst, all right? So the formula of a catalyst, okay? And the reason that a catalyst formula appears above the arrow as opposed to in the actual chemical reaction is because the catalyst is used in a chemical reaction, it's consumed, but it's also produced. So if we were to put the catalyst on one side, we'd have to put the catalyst on the other side, and then just like in math, if you have something on both sides, it can cancel out. So they put the catalyst here. And so the question is, like, why, if it is used and if it is produced, do we have to show it at all? And the answer is kinetics, reaction rates. So the catalyst initiates this change at a higher rate. And like the terminology that isn't super important now, a catalyst decreases in activation energy, right? Speeds up a reaction by giving an alternate pathway, an easier way to get from reactants to products so it can happen faster. And there's all kinds of ways to do that. So I just want to mention here, like as we look at this term catalyst, there's two parts to that definition. It speeds up the reaction, right? But it is not consumed in the overall reaction. We get it back. All right, and I'm going to use my space a little bit poorly here because there's a few other symbols that I want to sneak in. So I'll divide that off. And these, I think, are a bit more intuitive, and you've seen them before, or you've seen me put them on the board already. So I think you can have something like that, which is just solid, right? You can have an L, which is liquid. You can have a G, obviously that's gas. We've got now aqueous, right? Which we said is in water. And another symbol that I didn't put up here that I think we might just mention is that plus sign, right? And the plus sign literally means and, right? So when you see that in a chemical reaction, something and something else react. So this is kind of a legend for us, or a Rosetta Stone, to turn our word equation into a formula equation, and then now a balanced chemical equation. And that's where we need to head. So the word equation that I wrote and the formula equation that I wrote weren't quantitative for the law of conservation of mass. So we need to take note, we need to address balancing equations. Right? And in balancing chemical equations, we're adding coefficients to make the chemical equation represent the law of conservation of mass accurately, right? So we use coefficients, right, to make the equation obey the law of conservation of mass. And we're going to do this in a very specific way that's going to seem like it's a little more work, but in the big picture, it's better for science. So that's what we really want to watch for. So this balancing of equations you're going to see in the balanced chemical equation. So our third way that we're going to do this, which is the way we're pretty much going to skip to every single time, is to look at a balanced chemical equation. All right. And I do want to free up some space here, but in the balanced chemical equation, right, we are now obeying the law of conservation of mass. And we'll see how that works as we look at our example in a little more detail. The reaction we had written before was hydrogen gas and oxygen gas. So we've got H2 gas and O2 gas reacting to yield H2O, and that'll be gas for these purposes here. And we said there's an issue, like intuitively, even if you didn't know anything about chemistry, you might be able to say like there's two H's and there's two O's on this side of the arrow, and then there's two H's and one O on that side of the arrow. Something must be wrong. And so like that's good enough for some people, but like science is process oriented, and I really emphasize to my students the idea that you need to be able to show to someone how you got from an idea to an answer. Like an answer's okay, that helps one person, but a process can help everybody who looks at it. So like this is a mandatory step in my mind, and I really cram it down my students' throats that they have to do this, right? Show this work. So the way I have them do this is to set up a table of reactants and products. And this is super common for teaching chemical reactions. And I think many reactions don't require this intuitively, but I require it, right? This is process oriented. We got to show how this is actually happening. So in a minute here, we'll talk about reactants and products. But for right now, left side of the arrow, right side of the arrow, we're going to count up our pieces. So the pieces I have are hydrogens and oxygens. And on the left-hand side, I have two of those hydrogens. Those are our reactants. And I have two of those oxygens, two H's and two O's. And then on the product side, I have two H's again. That's good. The hydrogens are balanced. We've obeyed the law of conservation of mass. We ended up with what we started with. The oxygens, though, I only have one. So this is where we left off in our formula equation, and now we're going to pick up balancing. And again, I really want to emphasize, do this, okay? Do this every single time. Many people can look at this and say, I'm going to put a 2 there and a 2 there, and then it's going to be a balanced equation. That doesn't help anybody except the person who has to look and see if there's an answer. A random person on the street could look at this and say, oh, H's, those look okay, oxygens, those don't look okay. So when I ask my kids, like, here's an equation, is it balanced? The answer is supposed to be, I don't know yet, until we can show it to somebody, right? Anybody can look at this and say, oh, that's not balanced. So what do we need to do with this then is algebra, right? And that's scary at first, but the idea is pretty straightforward. We're using coefficients is what we had said. So something times 1 is equal to 2. So I take my product side, oxygen, whatever it has it, is multiplied by 2. So if I put a 2 right there, it applies to both the hydrogen and the oxygen, and I'll explain why in a minute. But now I have 2 oxygens, and that's good. Now I have the 4 hydrogens, and it seems like we've taken a step back, right? So oxygens, anybody can look at that and say, oh, oxygen looks good. Anybody can look at that and say, hydrogen doesn't look good, right? And we can go to the reactant side, find some multiple of 2 that gets us 4, which is 2, and put it in front of that hydrogen, right? So we've got we've got a 4 right there, and again, it's balanced. Anyone can look at this and say that's balanced as long as they did this stuff here, all right? Anybody can walk up to this and say, well, I mean, like somebody did some work, is it really balanced? But anybody can look at this and say, yes, that's balanced, as long as what happened here took place over here as well. I want to, so again, obeying the law of conservation of mass at this point. I do want to take a moment here to say what the difference is between this and the scary alternative that people often try and do. So this indicates you have 2 of these things, this H2O, 2 water molecules, 2 independent entities. I'm going to shy away from using an arrow there. So I've got a water, which is a hydrogen and an oxygen. I've got one of those, and I've got another water. Those are 2 separate particles, right? 2 independent entities. That's what this 2 means, right? Now, what a lot of people initially would like to do is say, oh, why would I bother using a coefficient when I could take that H2O, right, and just say, all right, I need another oxygen over there, and to balance this, I'm going to put a 2 there. And the problem is, when you change the chemical formula, you change the actual compound that you're working with, which is not what we're allowed to do, right? This changed bonds, it changed the compound. We're coming up with a specific compound. We can't just make up our new compound right here. So this would look totally different, and like I said, it's kind of a scary proposition to think we can do this. Hydrogen peroxide, you may recognize that as, looks like that. we have one particle there that is not water. And that's problematic because this reaction produces water. So you can't change these subscripts. The subscripts determine the chemical formula, and we spend a lot of time on chemical formulas and chemical names and working back and forth. So in short, coefficients, not subscripts. Coefficients are what determine how many of a particle you have, and the subscripts determine what the particle is. All right? So important stuff there. I just want to sneak in two last vocabulary words that we saw in that balancing, and then we're done with this. So, reactants and products. Reactants and products. I don't think this is a huge topic. I mean, it takes you like 30 seconds to say, that's what you start with, left side of the arrow. That's what you end with, the right side of the arrow. In fact, I'll write those words right now. This is found on the left side of the arrow. Right, that's what you start with. And the products are found on the right side of the arrow. Okay? And like if you need to, or if you want to break this into other terms, like I tell my students, reactants react to produce products, right? These are your starting ingredients, and these are your things that you make, right? So if you were baking a cake, you'd say like I've got sugar and flour and eggs and salt and milk or whatever. Those are your ingredients, the things you start with. And then your products are the things that you make. In that case, it would be a cake, right? So reactants, these are the starting components in a reaction, right? And then the products are your resulting species in a reaction, right? And when I say species, I think that occasionally people get scared because they're like, oh, that's a totally different species. That's just a science way of saying things, all right? And things isn't really a good enough word for describing things, species. So species is just saying the stuff you make in a chemical reaction, all right? So next we're going to have to take a look at different types of chemical reactions, and that's not going to be a small task.